Here we're going to try to derive the differential equations for regulated gene expression. So as you can see here, I have drawn a gene, an operator, a regulator, a protein, and a degraded protein. So this not symbol is a degraded protein. So to find the differential equations for gene expression, we're mostly interested in the change in this output protein P. So what we're trying to find is dP dt. And as you can see here, we have a degradation component. We also have the regulated component. And not to mention, there's always a background level of transcription. So let's just write that down. So we have basal expression plus regulated expression minus degradation. Okay, so let's go more into detail what all of this is. So our basal expression is simply constant. It's just the promoter's affinity towards RNA polymerase. So that is given by constant alpha naught. It's not dependent on anything except maybe the concentration of the operator, which we are ignoring since we are assuming it is relatively constant in this example. So the regulated expression will actually be related to how much of this regulator is actually bound to the operator. So it's going to be scaled by some coefficient alpha 1, and then we'll leave all of this blank. It's going to be some function of the regulator, though. And our degradation term is usually a first order reaction. And this is given by delta times P times itself. Okay, so now that we have accounted for all of the terms here, we gotta figure out what is in this term here. So suppose that we have, I'm just gonna draw a close-up again of the operator and some regulator R, which may or may not bind to the operator O, let's say. So this may be given by the chemical equation O plus R becomes a complex OR. So let's say that we are given a dissociation constant, Kd. So the dissociation constant is defined as the dissociated form over the associated form. So this is what our equation looks like right now. And we are interested in what fraction of the total operators is bound by the regulator, because that will change our gene expression, which makes sense. Suppose we have an activator. If there is an activator bound, then the gene will transcribe, versus if you have a repressor bound, then those that are not bound will transcribe. So we want to know this fraction. So we are interested in the complex fraction over the total amount of operator in the case of an activator, or in the case of a repressor, we are interested in the fraction that is unbound. So just O over OR plus O. So I'm just going to focus on the activator. It's pretty simple to get the repressor fraction. So just as a reminder, this is bound operator, and this is unbound operator. So let's work with the left side of the equation, which is the activator side. So let's use KD to derive what it is as a fraction of R. So the top part will become OR over KD. And then the left-hand side of the bottom becomes the same thing, over KD plus O. So notice how these O's can drop out, and this just gives us R over KD over R over KD plus 1. So this is our fraction of bound operator. So our unbound operator is very similar. If you do out this equation, you just get 1 over R over KD plus 1. Unbound. So this is the fraction that will be multiplied by our coefficient over here, and this is our function of R. So this is the fraction that is either bound or unbound to the operator. Now this will depend on whether or not this regulator is an activator, which will enhance gene expression, or a repressor, which will inhibit it. So let's just say that this is an activator. So we will use A for activator. So our concentration of activator over KD over A over KD plus 1. So this would be our ultimate equation for an activator. If you had a repressor instead, then you would replace this with a 1 and call that the repressor concentration instead. So that shows us how we can derive basic gene expression differential equations.